I'm going to tell you the bad news. So we're going to spend the next 55 minutes. I'm a great believer in HDI, but there are some dark side to the force here, or there's some failures, some traps that you can fall into. And it comes to do with quality control and reliability issues, particularly. So I'll kind of start with the fundamental improper drilling. So these vias are very, very tiny, and we use a laser. Well, that's an enormously more complicated technology than mechanical drilling that we've been doing for 200 years. And there's a lot of places you can fall into, and this is only partially dielectric smear, gouges in the resin, glass bundle tear off, nail heading, wedge voiding, glass fiber protrusions, hole debris. So one of the things I recommend, this is a laser drilling quality control system. It does not exist in the IPC. It does not exist in anybody's book. But if you're going to design a laser drilled hole, then I recommend that you copy this slide, stick it into your company's specs over the quality of those holes, because there are no standards about what that hole should look like. But there's definitely ways to make bad holes, and you only want good holes. And you can see down here, overhead, roughness, taper angle, voids, wicking, resin remains, and cracks. And here's some measurements, some specs, A, B, and C, control limits, and sample size. I recommend you copy this, and if your board has laser drilled holes in it, that this be checked out and enter your manufacturing specs in terms of what you want those holes to look like, because there are no IPC documents for them. I don't know if the European Space Agency has them or not. I don't know a lot about European specs. They do exist in Japan. This is actually translated from the Chinese, because this is what they use in Taiwan. And so it's not what the Chinese use, but what the Taiwanese use. And this is translated from the Chinese to the English. But I recommend this as a protection, that if you're going to buy the PC boards, have some specs that fabricators have to meet. They're not going to like you at all for having this, because they want to ship any old thing they make, and you don't want to buy and pay for any old thing. You only want to pay for the good stuff, not the bad stuff. Unfortunately, like I said, there can be a lot of bad stuff out there because they're so tiny, you cannot cross-section. So give up the hope of ever cross-sectioning. This stuff is way too small. It's like, well, let's cross-section the semiconductor. Yeah, good luck. You know, that's not how we do it in IC manufacturing, you know, kind of thing. Well, we're getting into geometries that you cannot use optical microscopic cross-sections anymore. So we're way beyond that. So the first thing is just simply the nature of the drilling. The other thing is the use of CO2 lasers. One of the problems with CO2 lasers is they can induce interlayer delamination because of the CO2 energy level. And so it's very critical, the narrow band of how much energy and pulses a laser can put out between removing the resin and creating so much heat it does micro delamination that you can't see. And you do not want micro delamination, because that will cause your board to fail in the field. And you don't want failures under warranty and things like that. It gives your company a bad reputation. But nobody bothered to tell you that you could be buying bad boards, you know, because not all boards are good and not all fabricators are equally as capable. But you say, so do they use an ultraviolet laser or do they use an infrared laser? If they're using an infrared laser, then you need to see the specs of the pulse width, the energy level, and the frequency of that laser with respect to the material that you're specifying, and whether or not the two, they've done some test runs to find the energy dispersal that material, it's very, very complicated. It's not the same as RPMs and a twisted drill, which is quite simple compared to the involvement of lasers. And believe me, HDI gets a bad name from the people that don't know what they're doing. They bought the laser, haven't optimized it, making terrible holes, and they're giving HDI a bad name because they don't know what they're doing. Yeah, they got the machine, but they don't know how to operate the machine because it's not like a mechanical drill. It's not a matter of RPMs and thrust. That's pretty simple for mechanical drilling. Laser drilling is enormously more complex. And they won't tell you that they don't know what the hell they're talking about. They don't know anything about this machine. In fact, you need demand to know that they know what the hell they're doing with that machine for your board in particular. And if you don't have confidence, move on to the next guy. There's plenty of great fabricators here in Europe that you buy from the good ones. You don't need to buy from the bad ones, even though they charge you less money, kind of things. And so one of the things is, okay, now we got the hole. Well, unfortunately, we may have resin smear and residue smear in the hole, which you can't discover this. These things are 5 microns across, or 100, well, 50 microns across. You can't cross-section this stuff easily. So what I always demand is that you have a coupon as part of the panel, off to the border, that has a daisy chain. And a simple 4 ohm resistance test tells, and if the upper and lower control limits are hit, they made a mistake, not in the drilling, but in the desmearing of that after metallization, and that you don't want any of those boards. Those have to be thrown away. You guys start over until that coupon reads the right 4 Kelvin resistance. You'll only pay for those boards because, again, you can't visually inspect this and you can't electrically test this. So you need to have a confidence that there is some process control mechanism involved that guarantees that failure mode hasn't shown up on your particular parts. And for reliability, I recommend a simple 288 solder pot float, that you take that daisy chain and you float it for 10 seconds, 10 times on this solder pot. So you take that thing, you drop it 10 seconds, pick it up, let it cool, drop it. And you use that 10 times, and that you have, that you're within the upper and lower control limit on the 4-wire resistance of those 200 or so microvias that are in a daisy chain. And the most accurate one is to have it thermal cycled, minus 145 to 145, after 3 preconditioning passes of 260 Celsius. There's the 10-second one is one that the operators can do. The other one is more that the quality assurance does, the 1,000 cycles type of thing. Again, with a test coupon that are part of the panel, and the test coupon must be returned to you along with the product. Okay, so yeah, you want to see the report. I also want to see the coupon. In case I want to test the coupon myself or cross-section it, they must return the coupon. Because otherwise, they'll test somebody else's coupon, give it a report of yours, and it's not your panel. I want to see the results from my panel of my boards that I'm buying and I designed, not his boards and his things. If they refuse to do that, then that's a good reason not to buy from them, because they simply don't want traceability from a legal point of view that they're not doing the job correctly. If they refuse to do it, it's a red flag that they know that they're not very good, or they're violating, or they're shipping you bad product. Because there's a lot of way that they will pass conventional electrical tests but fail in the field. And you don't want failures in the field with your name on it because it's tough to trace it back. And you're the one out the money and out the reputation with this stuff. For a 4-wire Kelvin, you can buy this expensive guy. I found in Taiwan this guy right here from a company called Pico Test. Right there, this is 600 euros. This is a fabulous 6.5-digit digital multimeter that's 4-wire, that's only 600 euros. And it comes complete with temperature and networking, and even a scanner card that you can add to it. This one right here is 3,000 euros. Equal. This one's 3,000 euros, 600 euros. I don't know if you know too much about them in Europe, but the funny thing is, their documentation is only in English and German. And I said, don't you have documentation in Chinese? No. But you're a Taiwan company. Yeah, but all of our customers are in Europe and North America. They're not asking for Chinese documentation. Well, that's okay. But it's a great, because I keep talking about 4-wire Kelvin, the 4-wire system, over and over again. In HDI, using these coupons statistically is the only way we know if stuff is good or not. Is not by testing the board itself, but by testing these coupons. And again, we learned this from the integrated circuit guys. On an integrated circuit wafer, they never probe the IC. Instead, they have parametric die, and they probe the parametric die. And only final electrical test do they probe the wafer. So we found that that's a better way to make a circuit board, is to probe a parametric coupon, not the board. Because all of your boards always differ. So we can create a coupon that doesn't change and matches the process. Because what we want to know is the process working? Is it in control? And at the final electrical test, we'll check the continuity of your design. But at least up until then, we know that there wasn't any process mistakes within that time frame. This is about via hole location. Calibration frequency is every 8 hours, the lasers are recalibrated. So one of the questions you ask is, all right, how accurate is your laser, and how often do you recalibrate the laser? One of the things is at least only every 8 hours. A plating check, 2 coupons per panel, 5 panels per lot. And again, the thermal stress, 288 solder, 10-second float, and then a 4-wire between the good or the not so good. This is because of separation. Oxide issues leading to delamination on the inner layers. De-smear conditions. So you go through, after drilling, you go through a sweller and a permanganate and a neutralization. How do you test that? Make sure that worked effectively. Again, there's a coupon for that. You can, see for these electron microscope things that the geometries of these microvias are very, very small. And that the permanganate can be done improperly, either immersion time or concentration. And when that's happened, there's melted epoxy, especially with CO2 lasers left. And the melted epoxy could be over an electrical connection to an inner layer, or it could only be partial. Well, that is going to fail in the field. It's going to pass assembly tests, but not reliability testing kind of differentiations. And so this whole thing about removing the smear, either not just on a through hole, but on the blind via, especially at the very bottom down here. That's a very critical area that's tough to get to. One of the things that was interesting was the improvement in material that was halogen-free over the traditional FR4. As the Japanese especially started demanding halogen-free laminate, the laminate got kind of re-engineered under modern times. And although slightly more expensive, was slightly better than the conventional FR4 that had halogens in them. So we've seen a trend towards improvement in performance with halogen-free materials. The problem is that the halogen-free has a different smear because they've changed the resin content. So depending on the materials you pick, have the fabricators done their homework in terms of adjusting the smear removal process to match this particular kind of halogen-free. The materials are not all the same. After drilling in solvent swell, there's a thing called mud cracking. In other words, the improper solvent swell cracks the resin. And as you crack the resin, you now introduce a field failure mode with that because it's the wrong concentration for that type of resin. Now, none of this exists in the drilled hole arena, because the drilled hole is so much bigger. But when you get really, really tiny with the laser drilled one, this stuff now all starts to pop to the surface. I don't want to frighten you away. I just want to sensitize you to your purchasing, that purchasing an HDI board needs more engineering attention than purchasing conventional multilayers. Be sensitive to the fact that it's a tougher technology and it can be done wrong. And you don't want to be the recipient when it's done wrong because it's your product, your board that's being done that way. Sidewall, no coating, the standard oxide coatings on the sidewalls. Metallization is a whole lot of fun in terms of being able to throw and plate into this little tiny blind via area. Etch voids and corner voids that exist there. Voids in terms of all sizes involved. These here are some more voids. Especially the microvia, one of the problems we have is that it's so small, it can trap a very tiny air bubble. And that air bubble can sit at the bottom of the hole, and it prevents the solution and plating and chemicals getting to it. But ever so small amount of metal does get to it. It'll pass all the electrical tests, but it will fail in the field. And what we're worried about is passing conventional electrical tests and then failures in the field, because that's under your warranty and under your company's name, not the fabricators. And avoiding this small hole voiding where you have, big thick boards and very small holes, which is why I advocate with HDI, you can learn how to design the backplanar multilayer with half the number of layers of the conventional multilayer, which minimizes the whole aspect ratio and that whole problem to begin with. And there's a thing called whole wall pull away. Well, the metallization pulls away from the dielectric afterwards, or overactive electrolysis, where you get peeling and blistering from overactive metallization of electrolysis copper. Inadequate desmeared drill debris, excess catalyzation, insufficient filtering of the electric copper solution, instability of the things, and excessive solvent penetration are all possibilities of this. Examples of excess conditioning and catalyzation. Because we're now moving into the era of what we call SAP, semi-additive plating and processing. And that's PC boards that has no copper foil on it. And so we're going to make a PC board, and we're going to make a 20 micron trace in space. Well, you can't make 20 micron. Well, you can't make really anything under about 50 microns on laminate, because laminate has a weave of the glass, and that prevents, it's not flat enough. So when we start getting below 50 microns, like the iPhone, you no longer use laminate. So all of you that have Samsungs and iPhones, there's no FR4 in your phones. They are all semi-additive materials, and they are unmetallized film. So they are vacuum laminated. They're nothing like the PC boards you're designing, unless you happen to be Samsung and iPhone designers. And that's because of the geometry. The iPhone 10 was a 30 micron geometry. The iPhone 11 is a 25 micron geometry. And so I think I have some photos in here this afternoon that show some of them. And so what we use is a thermoset film. Not thermoplastic, but a thermoset, but it's a film. And this film is vacuum laminated to an FR4 core. But all the HDI buildup layers the metal is added to it. So we condition the surface and we lay down electroless copper, typically about, we start with about 11,000 angstroms and move it up to about 5 micron, typically 3 to 5 micron. And we're extremely flat. So now we can do 50 micron, 20 micron, 10 micron, and we're moving down to about 5 micron traces and spaces. So we can do semiconductor geometry on that, and it's called SAP, semi-additive process. And that all of your Samsungs and iPhones have been the SAP for years now. But it's not copper clad. I mean, it's not the stuff that you may assume it is. Current density in terms of electroplating these holes, a thing called throwing power in terms of the aspect ratios. And this is a little bit more about aspect ratio, how it's calculated, what it is. Difficulty factor. The smaller that stuff gets and the higher the aspect ratio, the more difficult it is for us to physically get fluid. We have to get fluid into these things. And if we don't get the fluid into it, we can't electroplate it at a uniform. And the copper isn't thick enough, it's going to fail through normal use. And so here are some of your iPhones and Samsung in terms of complex designs of blind and buried vias and stacked vias, et cetera. Some via formation. This is an example of bad via formation. You notice how they ripped up the copper layers with the laser, and they've broken the layers of the glass apart. You don't want to see this in your boards, because this stuff is headed towards field failure, under warranty kind of stuff. Blind via plating problems. This is FR4 resin-coated copper versus FR4 that has glass and prepreg. So again, selection of material is better if you go with newer generation of materials that are never used in a multilayer. So you must start using materials that you've never used before, because there are materials specifically designed for HDI. You can't use them in a multilayer, but you must use them in an HDI. That's another thing to learn on HDI is there's a whole new set of materials that you've never seen before, but they are better, more reliable materials. And if you don't know about the materials, then somebody needs to come out and kind of educate you on why the materials are different and why they're better, and why you must design with them and not the materials you're used to designing with. These are just different pictures of good microvias that are properly plated and designed and positioned. There's good blind via plating. it's kind of uniform. It's not colluded. This is good filled microvias, in which, see, that's totally filled with the different chemistry that will fill that up, solid copper. This one is filled with a dielectric and then capped over. This is okay, but this costs a lot. This technique right here of using the fill, unfortunately, it's a different chemistry than for through holes. So one of the people that I work with, I'll talk about on Wednesday, the Smart Factory, they can empty their machine in about 3 minutes and take out the standard high throw chemistry, bring up the via chemistry to do the via plating, and then take it out again and bring back the commitment. So the same machine has 4 or 5 different kinds of solutions they can bring in and out. Because to make the modern HDI board involves 4 or 5 totally different electroplating chemistries. Nobody has one magic chemistry that does everything. If you want it done right, you have to employ 2 or 3 or 4 totally different chemistries. And what they've done, instead of having 2 or 3 or 4 machines, they bring it in and out so rapidly they can use the same machine with the different chemistry and different electrical parameters. I'll show you that on Wednesday. And that's all driven by computer control and a smart factory concept in which we've got an electrical model driving the actual manufacturing line. There's a failed superfill. For one thing, the laser had too much energy and went down into the target land. Don't want to see that, but if you've got too much energy on the laser, you've got to remember, a laser has programmable energy, and that has to be programmed in for your material and your thicknesses and your design, that somebody else's HDI board may require a different laser recipe than your boards. So one of the things you want to ask about to purchasing is, what is the process for my boards in your factory? Because a course I went to, a guy told me that there's, unlike mechanical drilling, where everybody has the same drilling parameters, laser drilling, it can vary board by board by board. So, what's my recipe? If they say, oh, it's the same as everybody else, be cautious. Because if the answer is it's the same, then they don't know what they're doing, because I guarantee you it's not the same. If you've chosen MEGTRAN 6 instead of Ventec polyimide, totally different laser parameters required, both in energy levels, pulse repetition, and pulse duration. Laser drilling is quite complex in terms of all of these parameters that you've got available to you. So you can easily do it wrong. Easy. When you do it wrong, you've gone into the target land. You don't want to see that. Here, this thing, look how much copper plated up there. No copper down there. The whole metallization and copper plating failed. Guess this will pass electrical test. So this could be shipped to you as a good via. It's not a good via. It's going to fail. And yet you think it's good. So when it fails, what happens, in order to prove that, I actually took customers' boards and I wire bonded shorts on the inner layer, okay? So I know exactly where the shorts are. Built the boards, we shipped them to them, and we watched them go through assembly, and the boards got shipped off as failed in assembly test. So they went over to technicians, and the technicians were working on it, and eventually he puts a reject tag on it. We run over to read what's on his tag, and the tags always say, too much time. And what happened was, I cannot find the failure, and I've exceeded the time allocated to repair this board. So we throw it away, and the reason we throw it away is it took too much time to troubleshoot it. So I don't know what the root cause is. And so I proved to management that that when a printed circuit fabrication sabotages you, you can never pin it on the printed circuit fabricator, kind of thing. You know, you have to have extra guarantees that you're getting a good product. Not that I'm paranoid, but you know, a lot of bad stuff can be shipped as good, and it comes back on your back that it was a bad design or bad something, and it had nothing to do with you. It was bad fabrication or bad assembly. You need to be paranoid. I forget whoever quoted this saying that, you know, only the paranoid survive or something in the long run. Well, if you're going to do HDI, be very skeptical. Be very, very skeptical all the time. Protect yourself. You know, if you're going to use it, great, but make sure that you're not the result of somebody that's not doing their job correctly, and somehow it's blamed on you. Not your fault, but you know, you know, if that gets shipped to you and nobody in your company had a way of discovering that, it might never be attributed to the fabricator. That's what it should look like. You know, it should look like that. So it's a good fill. Thermocycling tests, like I said, this, you know, 500 cycles of minus 45C to 155C type of thing. Something like this, past that. One like this, I test to destruction. This will typically go through 2,000 cycles to 3,000 cycles. The through holes will fail after 400 to 500 cycles. The micro via will go to 3,000. And in fact, a lot of times, companies send them back to me, and they said, we've gone 4,000 cycles, we're going to stop. We're not going to test the destruction that you wanted, because we don't know how long your boards are going to be on this machine, and we're losing money, you know. So I said, okay, 4,000 is good enough. You know, if it hasn't failed after 4,000 cycles, yeah, it's pretty robust. But a lot of times I pay for a test to failure, so I actually know what the failure numbers are. And a lot of times I get HDI stuff back that said, we can't test to failure. We did a model that we indicate that this will fail after 7,200 cycles. So I'll take the model approach. You did 4,000 real and extended the model to 7,000 kind of thing. But if they're done right, they're really, really robust. Misregistration on solder mask, because the vias are so small, especially if we go landless. There's no via to look at it. There's no pad to look at at all. It's really tight. Concern over stacked micro vias. We're having a new problem on military and space in that anything over 2 levels stacked vertically are failing in space or failing in the field. So we have a new test method, 650 2.6.27a, that is effective at discovering these latent defects. And we're still investigating the root cause. But right now, we published in the IPC a warning: do not stack vias on mission critical products more than 2. So if any of you are mission critical and you've got more than 2 stacks, immediately go back and change the design to only 2. Go 2 plus 2 plus 2. If you've got 3 or 4, test them using 2.6.27a and see if they pass. We're seeing 30 to 40% failure on mission critical. I shouldn't say military aerospace, I should say mission critical boards, whatever mission critical means. They don't care in mobile phones if they fail because they only have a 2 or 3 year life. But the mission critical stuff can be 15 to 30 years. And they want to make sure it works after 20 years. And I'll guarantee you it will not work after 20 years if it has one of these defects. And if you want, you can get a 60-page white paper that we put out on what the problem is, how it came about, how long we've been living with it for mission critical And we're working with the European Space Agency right now on root causes, solutions, and simulations to figure out what's going on. But stacked microvias are right now a problem that we haven't quite figured out. Here are successful stacked microvia qualifications. These things pass 30 cycles of this IPC 2.627A. So we have some examples of 3-stack and 4-stack that did pass. But there's only there's only 7% of all microvia fabricators apparently have the technology to pass this. Not all of them are. And they're reluctant to test to this spec because if they fail, they're going to lose all their business until they figure out the root cause. So there's kind of a war going on between this new spec and fabricators, whether or not fabricators want to cooperate, because they're frankly going to lose business. So right now, the one that we're working with, he's getting 40% returns on the most expensive PC boards that are mission critical because they're failing this spec. And he's got to take them back and give credit. So he's losing a lot of money. There's an urgency to figure out why this is happening and why we're seeing it the last 3 years. So the last part is selecting a HDI vendor, especially for reliability. Most reliability is based on some kind of test vehicle, like liquid-to-liquid thermal cycling, rows of holes, or HATS coupon or IST coupons. And so this was my first parametric board that I designed in 1983. And that's because I had to train 16 Chinese engineers that knew nothing about printed circuits. And in training them about printed circuits, they wanted to make real PC boards. And I said, well, that's not a good idea because PC boards are so different. Let's kind of make a composite PC board with all different kinds of technologies on it, some of which are easy and some of which are very difficult. And you can make the same PC board over and over and over again until you can make all the technologies on the PC board correctly. So we did that in 1983. And that worked very effectively because at first, they only got 10% to pass, but then they got 20% and 30%, and eventually it came to 100%, and they knew how now to manage all these things. So that was my first inkling that don't test a vendor by having them build your board. Have them build something that's much more complex and difficult than your board. If they can make that successfully, then they can make your board successfully. And a board that you specifically designed to be a test vehicle for them, so you know how to interpret it, and you can send it to different people. And it doesn't talk about the intellectual property of your design, but it does have the elements on there to see whether or not they can pass that. And so in Hewlett-Packard, by '87, we had this much more elaborate in that we had 12 different sets of these coupons. And we would ship them an entire panel of these things to build. And then we would bring them back, and we had designed this so this could be tested on a matrix bed of nails through continuity testing. So we just flop these things down and run it through our program, and it would write us a great big statistical report on what their imaging capability was, their drilling, their lamination impedance of multilayers and things like that. That was very easy to benchmark what was their capability. Their salesman told us the capabilities here. Actually, measurement of their capability was something else. And so based on that, by '92, the IPC created what we called 9151. And the IPC 9151 is a benchmarking technology that's intended for mission critical and advanced technology PC board that's very, very well. It's been in existence since 1992. And it works with a company called Conductor Analysis Technology, CAT, that built very special testing equipment. And so if you go to the CAT website right here, it gives you all the fabricators around the world that have successfully built the IPC benchmark and when they successfully built that. Typically, the McDonnell Douglas, Boeing's, Lockheed Martin require that they successfully pass this benchmarking, and they requalify every 6 months. So they, and that there are coupons on the board that match this benchmark, so that every single panel that Lockheed Martin buys or Raytheon buys can be traced to this statistically significant benchmarking. It's a really, really well-designed, excellent quality reliability control system that works quite well. And it works because it's built out of these 2.5 centimeter square multi-layers that you notice has all kinds of stacked vias and drilled vias and sequential laminated vias. And it goes up to 24 layers. There are all kinds of design libraries. You can see different diameters, different laser diameters, conductor widths, number of laminations. This one goes through 3 laminations because 3 buildups, layer count. And these are the machines that they're put into. This is one that a fabricator has himself. The coupons kind of look like this. You solder on an end thing. You put them in this tray. Then it goes minus 155 up to 190 Celsius for a cycle, and then back down again, all under 4-wire connection. So if any time during the cycling or transition an open occurs, it's captured with that. So the coupons typically have 4 nets. So since you have 4 nets, you can change the design rules to a different set of design rules that you're testing. It also has the CAF coupons there, in case you're interested. And like I say, a chamber full of 36 coupons costs about $2,500 US for 500 cycles. 500 cycles is good enough, but some of you, a mission critical, may choose 1,000 cycles, in which it'd be $5,000 US for 36 coupons, tests like that. This is one of my reliability tests, and you can see my panel has a CAF. It has 4 ones, 5 of them, and then it has a solder joint coupon. So this one up here is going to test for solder joint reliability with a dummy BGA that has a daisy chain in it. We solder it to this one. And so there we're testing the solder joint. And you can kind of see the vendor A, vendor B, and material and fabricator and quantity it goes through that. And then around here, right here, these coupons right here, these are the standardized coupons that are in every single one of our assembly rail. So we manufacture about 60 million circuit boards a year for our products. And all 60 million PC boards are traceable back to the coupon during fabrication and assembly electronically. So since we're automotive electronics, if BMW or Mercedes, and we supply all of BMW, all of Mercedes, all of Audi, all of Honda, all of Toyota, all of Nissan, all the way down to the Indians and the Russians by our automotive electronics. If there's ever a field failure, you know, they can give us the code, and we can go back to when it was manufactured and fabricated and even find coupons. Because if there's a field failure in an automobile, we have to go through holy hell to prove to the automotive company that we've got this under control and it won't happen again. I mean, you think the military is tough. There's nothing like Mercedes or BMW or especially Toyota. They're, you know, so, because that means money to them. IST is the other one, interconnect stress testing in 1994. This is an accelerated test, but instead of using external heat, they pass high current through holes and heat the board up internally. And so this is a little funny, and a lot of people like to use it because it's quick and cheap. It's debatable whether or not it's simulating field failures, because the temperature is induced internally, and in field failures, the temperature extremes always come from external. And this one is an internal, and this cannot go below room temperature. And the whole negative transition creates all different kinds of stress activities that this can't test for. So there's a lot of debate about this. I won't go into the debates about this test methodology, but you see, it goes from room temperature hot and then a convection cooled. The problem is it can't go hot enough. We found that in microvia, we now have to go at least to 230 Celsius, and this can only go to 190 Celsius. And so we're getting a lot of failures in nuclear submarines and failures in atomic warheads and mission critical stuff that's failing because it's supposed to sit, it's supposed to be okay for 10 to 20 years, and it's dying after 3 years. And it's because we can't go high enough in temperature with this IST testing, but we can go high temperature under conventional means of testing. So it's well, there's an enormous amount of debate. It's going to probably be solved with the new European Space Agency's testing criteria that we're working with now with the European Space Agency. Hopefully we'll kind of settle all this because we're kind of involved in politics of what people bought what machines and how it works and new materials and new design. And it all involves profitability, so people are very sensitive about all of that. With that, we're almost so I don't want to scare you off of HDI, but I do want to sensitize you that you've moved into a more advanced set of technology, and it's really, really great, but it also really has potholes and cracks and crevices that you can fall into if you think everything's going to be fine, because that's the way it's been in the past. No, you stepped into something new, you need to have purchasing and quality engineering step up to the new demands that this is going to cause. Otherwise, it's going to come back and bite you in the butt if it fails in the field and with your customers, because your customers don't expect that from you. They expect a product that meets all the specs in the lifetime that you guaranteed it. And you've moved into an electronics technology that maybe you don't know about. What are the shortcomings? How can it not live up to its expectation? Well, there's a lot of areas. If you want to read more about this, the current edition of the Printed Circuit Handbook, the reliability sections went from 2 chapters to 9 chapters. So the latest edition of the Printed Circuit Handbook has 4 times more area devoted to solder joint reliability, through-hole reliability, and blind via reliability than any of the prior ones because of the complex nature of the interaction of the defects. And it's written by what I consider a world expert, Raza Ghaffarian, on the Jet Propulsion Laboratory. So the 9 chapters are written by the world's foremost experts, including information from Werner Engelmeyer, who is a very brilliant reliability scientist that had a heart attack when he was scuba diving off Israel. So we lost him, but his work was outstanding, and we brought Werner Engelmeyer's reliability information into those chapters. So you have not only what everybody else is doing in Bell Labs and in Bell Northern Research and in Siemens and things like that, but you also have several other experts, because there are deviations in reliability based on who's the expert. It's not total consensus on everything, but enough that you can pick and choose which expert are you going to be in their camp or not, kind of thing. Also, the design section of the printed circuit handbook went from 5 chapters to 15 chapters. So the design portion of the HD handbook got enormously bigger to handle HDI and these new materials and these new design techniques. Unfortunately, the book is 1,900 pages and weighs about 8 pounds. I mean, it should have been 2,200 pages, but McGraw-Hill cut us off at 1,900 pages. So we had to throw some older stuff out of the book in order to make room for the critical new stuff, which means if you have the 6th edition or the 5th edition, keep it, because some of the things in the 5th and 6th edition are not in the 7th edition, because we had to put the new stuff in, and we had a page limit, so we had to take important old stuff out. So don't get rid of your old ones. But the only book you can depend on is the printed circuit handbook from McGraw-Hill. There is no other, unfortunately, there is no other book published in the entire world that you can believe or you can trust. And it's the textbook we use now in Michigan for training the electrical engineers. We actually use that as a textbook because there is no textbooks. And like I say, it's this thick and weighs about 9 pounds. And unfortunately, it only comes printed. I have the only electronic version in the world because I'm the editor, and I'm not supposed to give it to you, although I carry it around in my computer, which means give me enough beer and you have a big enough problem, I might email you that chapter, but I swear you never to tell anybody that I gave you a chapter electronically when you're supposed to buy the book. But I do think that McGraw-Hill will sell you it on a CD, but it's the same price as the book. I recommend the electronic version because then you can carry it around anywhere. Unfortunately, it's still black and white. It should be color, but it's black and white. And that's because this is the 50th year. The 7th edition, 2016, the first printed circuit handbook was 1996, edition 1. So this is the 50th year that we've had the printed circuit handbook. And so there's a big hoopla because it's one of the biggest selling handbooks McGraw-Hill has. It's like enormous in size, but it's also, this is 50 years. And I have all of the editions from the first one in 1996, 1976. First edition was 1976. No, 1966. Oh, 1966 was the first edition. So I have them from 1966 to 2016. And they went from a book this size to a book that's about this thick. And so I have cataloged all the stuff that we removed. And we have removed 2,000 pages, none of which is obsolete. And so I've been talking to McGraw-Hill, let's publish a book of the 2,000 pages we took out of the PC handbook that are still relevant, still being used, but we don't have room in the handbook anymore. Because people don't realize that we have removed 2,000 valuable pages, not obsolete pages, valuable, in order to put the new stuff in, which is why I keep complaining. We're using technology that's 60 years old. Yeah, if you go back and read the 1966 book, if you go back and read it, that's still being used today. It's not obsolete. It's just like, which is why there's something kind of wrong if you have 60-year-old technology, because in electronics, nothing is 60 years old, I mean, concept-wise, unless you're still designing with tubes, anybody here designing with tubes? I do. I like to design with tubes, because that's how I started, it was with vacuum tubes. So when I got my advanced degrees, the integrated circuits I had 6 transistors on them. Now they have 6 billion. So I've gone from 6 transistors per chip to 6 billion transistors, and back to using tubes again. Unfortunately, I had to buy the tubes from the Russian or the Poles. I can't get good tubes anymore. Vacuum tubes are a thing of the past, but they're a lot of fun. With that, we have a lunch.